the receiving end power, which we're calling SR, as a function of the voltage angle at the phase angle at the sending end. Which actually, we gave that a name. We call it delta. All right. So this is shown in the book as equation 244. Also, one other thing that I am going to do today, I am going to start assigning homeworks. Okay? And actually, you know what? Maybe, so I don't forget. Well, I'll do it again. Remind me if I don't remember. The homeworks will start with the second half of Chapter 2. I'm not going to assign homework for the stuff that we already did the quiz on. But we'll start from the stuff that will be covered by the quiz. That will be next Monday. And the homework will be due on Monday, and if you have questions, you can come to me about that. In previous iterations of this class, I haven't assigned a lot of homework, only because the examples themselves get relatively complex. So I do feel like the homework is a little bit of a supplement. If you can get all of the examples and really understand those well, the quiz and the exam problems are very heavily drawn from those. As you can see, right, the first quiz was pretty close to one of those first examples that we did. Okay, so equation 244. We know that the receiving end that's our basic starting point. We're going to substitute in the equation we had from the previous calculations we did. We know that that current there will be equal to the difference between the voltages divided by Jx. All right, and this value right here is represented as angle delta. This right here is a 0 degrees. Right? We've assumed that the receiving end is the reference for the phase. Okay, now what we can do is we can split this up into the real and imaginary components, which will give us bless you. And so where do we get that from? How come the VR squared component only shows up in the second part of this equation? And that's because if we take a look at the first line, you'll see that the first VR, right, will not be associated with any J value, won't have a J coefficient. The second one will. And so what we end up with is that little additional piece being tagged on to the imaginary component as minus VR squared. Okay, so now, next question. So what's the maximum value of real power that we can transmit along that line? Assuming that all the voltage magnitudes stay the same, assuming that the reactance along the line stays the same, everything else stays the same. What's the maximum value that we can transmit for PR? Right? That would be when sine of delta is equal to 1. Right? If I cover this piece up, I can't reach it. But if I covered that piece up and made the sine of delta a 1, that's the maximum power that can be transferred. So the maximum power transferred is going to be PR max equals VS VR divided by X sine of 0 degrees, which is a 1.
Sine 90?
Sorry about that. Sine 90. Okay, so now moving forward with this, let's make an assumption. Let's neglect real power for a second. And examine the case when delta is equal to 0, which actually we wouldn't have to neglect real power because that would be the case where PR is 0 anyway. Okay, so now what would our QR value be? So QR would be equal to, referring to this back up here, VS VR divided by X cosine of 0, which that would be 1, minus VR squared. Yeah, now I was going to put that. I didn't remember that. PR squared divided by X. And then that simplifies to this right here where we have VR times VS minus VR divided by X. And what we see is that there's no delta in this equation here. Now, why are these equations something that we should even care about? So mainly I'm saying this one right here and this one up here. The reason being that we can represent PR and QR, or we can approximate them for small angles of delta using these. Well, does anyone know what the approximation is for cosine of an angle and sine of an angle for very small values of that angle?
For sine of angle, so small angle approximation is sine of x approximately equal to x for small values of x. And then cosine, I think, approximately, I'm not sure.
Yeah, that one's approximately a constant. So for small angles So for small angles, of delta, so the first one is sine of delta is approximately equal, like you said, to delta. Cosine of delta is approximately equal to 1. So those are two approximations that we can use. And so now, can we represent PR and QR as approximations for the case where delta is very close to 0? We can, and what we'll see is that this is relevant because the phase difference between two adjacent buses is normally going to be pretty small anyway. So this is not an approximation that's going to work in all cases, but it's one that gives us a good starting point for how transmission line is going to work. So we have PR is equal to, or I should say approximately equal to, VS, VR divided by X delta. Then we have QR is equal to the version we have up here, VR over X, VS minus VR. And I'll include a 1 just to show that's where the approximation was. Okay, so now, looking at the equations above, so looking at the equations above, what single factor, and it's different for either. Okay, what single factor has the greatest effect on PR and what has the greatest effect on QR? So for PR, we see that angle, there's a very strong relationship between, we could say PR is predominantly a function of delta. Okay, and we can say QR is predominantly a function of the voltage magnitudes at both of the buses. So what we'll do is we'll call this the strongest strongest or the predominant relationships when delta is approximately equal to 0, yes.
What is the X represent again?
X is the transmission reactance, or the reactance along the transmission line. I think in the previous slides we were calling it XT, and I dropped the T somewhere along the line. Okay, now, so how can we visualize So how can we visualize the relationship between PR and delta? We can graph it. What we'll see is, and this is from figure 218 of the text, I'm going to make the y-axis here, I'm going to say it's PR over PR maximum. That means that now the y-axis will go between 0 and 1, right? Where the maximum value was this up here, right? That's our PR maximum. So again, so y-axis will go from 0 to 1. So 1, 0.5, 0. And on the x-axis, I'm going to have the delta. So we have 0, 90, 180. Our approximation zone that we are looking at is in here. So these two equations the approximations that we define right here, those are going to work inside of the yellow circle, only for when the delta values are relatively small. Okay. Okay, next. So what was the objective of that last section there? Was to simply characterize the relationship between both ends of a transmission line, but mainly what it was trying to get at, and we'll see this relationship come up over and over again, is that strong tie between voltage magnitude and reactive power, real power and voltage angle, okay? When we go to load flow analysis, different types of nonlinear analyses, when we're talking about control problems, we'll keep coming back to that. We'll say, assuming that the voltage angle difference is small between two ends of a transmission line, we can control our reactive power predominantly by manipulating the voltage magnitude. We can control the real power by predominantly manipulating the voltage angle. Okay, per unit analysis. Try to make this bigger. So there's certain topics, this is from the old set of notes, there's certain topics where, there's really no advantage to rewriting what's already been written. So this does a really good description. It's from the old version of the textbook, the Granger textbook that we used to use, but this is really a topic that's universal. So what is per unit analysis, or per unit quantity? So it's a way of representing values for a power system or for any engineering system, where instead of putting the value in volts or amps or watts, we simply refer to it as a percentage of whatever the nominal or the rated value was. So if I tell you that a given transformer has a line to neutral rated voltage of 120 volts, and then I tell you that the voltage across the terminals is 110 volts, then the per unit value would be 110 over 120. Okay? So, and I guess it would be close to 90-something%, right? So you would say either it's 0.93%, or you would either say it's 93%, or what we call 0.93 per unit. And per unit is essentially not a unit, if you understand what I'm saying. When you do the calculations, you don't have to take into account any units. It's a unitless measure.
And the ratings and manufacturer's rating?
It's the manufacturer's rating, or it can be another rating that you're using in order to get units, components within a system to agree with one another. One of the things that we'll see is when we use per unit analysis, or per unit values, all of the components need to share the same power base or same power rated value in the system in order for the calculations to work. So we have to do conversions sometimes. If we have two transformers, they can have different voltage bases, that's fine. But if they have two different power bases, we may need to do a conversion, recalculate what the voltage base would be or what the voltage value would be based on the new power base, such that they agree with one another. And we'll do an example of that so you'll see what that means. But in more concise terms, the ratings will normally be given by the manufacturer. We may use those ratings exactly, or we may change them slightly in order to fit our purposes. The main thing you have to keep in mind here is that agreement is what is most important. Okay? You don't want to lose the value of what you had initially. If you had 110 volts and you go to per unit, you want to eventually be able to go back to 110 volts. And there's certain ways that you can manipulate the bases to make that happen. But if you don't play by the rules that we're going to talk about in a second, you can lose your value. And when you go back to voltage, right, you might end up with 112 or 115 or some different value. Assuming that you do everything correctly, you can go from actual units to per unit, back and forth without there being any unexpected changes. So, how can system parameters be represented without the need for units in per unit? All parameters and states will be represented as the percentage of a nominal value. And in the beginning, what we'll do is we will refer to all, we'll put this little PU superscript associated with the voltages and the currents. As we get later on into the class, we'll start to drop that. And actually, we'll get to the point where all of our values will be in per unit, so we won't have to specify each time sorry, go for it. This is in per unit, that is in per unit. Voltage in per unit is equal to the voltage in actual units divided by whatever the base is. Same thing with impedance, same thing with current. You have to be careful whether your voltage is a line to neutral voltage or a line to line voltage, because you want to use the appropriate base for that, and they'll be different, okay? If the line to line base is 208, the line to neutral base will be 120, right? You use the same conversions that we learned about last time between the line to line and line to neutral voltages.
What is this subscripts there? Are those T's? What is that?
It's just T.
What does it represent?
Actually, it's I. It's for bus I. For a system, it's necessary that we define 2 of the 3 bases. We don't necessarily have to define, well, not unnecessarily. We can't define all 3 because that would be an over-constraint. Right? We use Ohm's Law to relate the third to the other 2. So we define the voltage base and the current base, or we define the voltage base and the impedance base, etc., etc. Now, these conversions here, essentially what they show us, on the left-hand side at the top, we have a single-phase power base divided by a line to neutral voltage base. That gives us current base. If we have a 3-phase power base or a line to line voltage base, we need to use these conversions in here, and that gives us a new version of the same expression. So the rules that we use to convert the bases are the same as the rules we use for voltages and powers early on. Remember, we said single-phase power is equal to 3-phase power divided by 3. So we have single-phase power here. If we want to convert it to 3-phase power, we insert 3-phase power divided by 3. Line to neutral voltage, we want to go to line voltage. So what's the relationship? Line to line voltage divided by square root of 3 gives us line to neutral voltage, right? And so these 2 conversions, this one is associated here, this one is associated here, take the I base, which is initially in terms of single phase power base and line to neutral voltage base, and puts it in terms of 3-phase power base and line to line voltage base. Does that make sense? One thing that can be confusing here is the terminology. Okay? You need to be really familiar with the terminology in order to understand these differences. If line to neutral, line to line, 3-phase, 1-phase, delta, Y, if all those terms start to sound the same, it's going to be very difficult for you to pick out the individual differences between these bases here. The reason why we need different versions of the equation is because of the way it might be presented to us. We need to be able to define the base for all the contingencies. Z base can be equal to the line to neutral voltage base divided by the current base, or line to line voltage base divided by the current base times square root of 3. Again, we're using that same conversion in there. So this is one thing that I am going to ask you to review on your own. The reason why I say that, though, is because the middle part that's grayed out is not necessarily something that I'm going to be testing you on. Okay? What I'm going to be testing you on is the ability to use this, to use this, to use this, to use this. You understand what I'm saying? You need to be able to use the endpoints. So if I give you a problem and I say, give me the voltage, give me the impedance base for a system with, or a component with a line-to-line voltage base of 208 and a single-phase power base of 100 or 2 megawatts, right? You need to be able to combine these together in order to tell me what the Z base is. In the end, units is the thing that guides you, okay? Per unit, again, should always be no units. So the numerator and the denominator should cancel out. And like I say at the bottom here, there's a million different ways to represent those conversions. I only showed 4 different permutations. I didn't show you line-to-line voltage combined with single-phase power, or et cetera, et cetera. So I think by becoming familiar with those equations, when we move into some of the homework problems and some of the example problems where we work in per unit, that'll also help you become more familiar with it. But it's the basis of it is really nothing more than the conversion between three-phase power and single-phase power, which is easy, divided by 3, and the conversion between line-to-line and line-to-neutral voltages, which again, multiplied or divided by a factor of square root of 3. Okay. So a good way to follow up on this is to do an example. So let's do an example using per unit values, and we'll show exactly, what are some potential pitfalls that you might see. So section 2.6 from the text is ratings, base values, and per unit quantities. Okay, and I just reminded myself to include those notes from the old version in the folder that we're using now. All right, so let's jump straight into it. Calculate the values below. It asks us for the per phase voltage, load impedance, load current, and apparent power. Let me bring this up in the book. Because what I should actually say is calculate the per unit values below. It's it's an important part of the problem statement. So we have the per phase voltage, we have the load impedance and the load current, and then we have the apparent power. So again, all of these in per unit. Don't, not that you would get confused, but the terminology of per unit and per phase, right, seems similar, but they have very different meanings. Right? Per phase is when we take a three-phase system, we assume balance conditions, and we analyze a single phase only, right? That's per phase analysis. Per unit is when we take the values that are in actual units, watts, volts, amps, ohms, and we convert it using a set of bases or rated values, all to percentages of those rated values. You can perform a three-phase analysis using per unit values. You can perform a per phase analysis using per unit, or vice versa. Per phase, not using per unit. They have no relation to one another. All right, and so the values that it gives us it tells us that the line-to-line voltage base is 208 VRMS, and it tells us that the three-phase power base is 5.4 kilowatts. And it's calling back to example 2.7 for the other values. So in example 2.7, it tells us also that the voltage line to line is equal to 208 volts. It tells us that the right, those are all from that previous example. The one that we did the power factor correction for. All right, so how do we handle this? I drew a picture, but I don't think we really need to draw a picture. Well, it might make things easier. So let's draw a schematic in per phase, which is essentially the answer that we got from example 2.7. So what we got when we did 2.7, after we had completed it, was we ended up with something that looked like this. Right, we saw that the V source was equal to 120 volts, line to neutral, right? ZL was equal to 10. That's already written above. Our IA or IS ended up being 12 with an angle of negative 37 degrees amps. And I think those are all the values that we got. Let's go back to it for 1 second. We also got, right, these two values. So the apparent power was 1152 plus 864. Right, that value we also had. Now, how do our bases relate to this figure? We're given two different bases, right? We're given the line-to-line voltage base. So we can imagine that as if we, and I'm drawing the green as sort of just right, if we had our source connected in delta, then the voltage would be, here would be 208 voltage base. And also, if our load were three-phase, then the power consumed by all three phases would be 5 kilowatts. Okay, so the voltage and the power bases that they gave us don't line up with the values that we have, right? And they also don't match up well with doing this analysis in a per phase form. So there's all those equations and versions, like if you saw the PDF or the Word document, there's all those different converted versions of the bases. However, the simplest way to handle problems like this is just to convert the bases to whatever fits the analysis that you're using. In this case, it's per phase. We can go ahead and just take the voltage line to line base and convert it to line to neutral. So what is that going to be? So we'll calculate our voltage line to neutral base. And that will be equal to what? It's the same conversion, yep.
208 divided by 3.
Exactly. Voltage line to line base divided by the square root of 3, which will give us 120 volts. For our power base, we're only, in per phase analysis, we're only dealing with one of three phases. So we're going to want to use a single phase base as opposed to a three-phase base. So our S single phase base will be equal to our S three-phase base divided by 3, which will be 5. I'm just going to leave as a fraction for right now. 5/3 kilowatts. Later on we can make that into a decimal. So those two conversions that we did right there That's the same thing that we did here. Okay, so although these versions seems like a lot of math, seems like a lot of values, a lot of things being connected together, converted, it's really, when you break it down piece by piece, it's just applying stuff that we're really familiar with. Okay, and then once we have the values,
Shouldn't be 5.4 thirds kilowatts?
is it 5.4?
Yeah, they have the three-phase base with 5.4. Maybe you wrote it a little bit up there.
Yeah, I apologize. I wrote 5 somewhere and I copied that value. All right, so this is 5.4. Okay. So, lastly, we should calculate our current base and our impedance base. Now we can calculate the others. So we have the 2 minimum. We can calculate the others. So, Z base and S base. So here is where you have to be careful that your units match. And again, to refer back to this, which I will post in the online on the website. Here you have to make sure that you're using the corresponding values such that everything matches up appropriately. So, which one of these cases are we dealing with? For the current, okay, we're here, right? We have a single phase power base and we have a line to neutral voltage base. So that will give us, so V, line to neutral voltage base, divided by, yep.
You just switch back to the iPad.
Oh, yeah, sorry. That's why you got to call these things out. Thank you. And actually, I meant to write I base and Z base here. Okay. So V base line to neutral. So that'll give us 120 volts over, what's 5.4 divided by 3? Can someone give me that value?
Yeah. .8 exactly.
Mm-hmm. There we go, 1.800. And I have this upside down. Sorry about that.
So the bases, the base values, that's the things that we're gonna relate everything to when we do the curve.
You'll see there's a second step to this. We haven't, the final step is to actually take those values that were given to us, the actual values, and put them in terms of the bases. So when we do a per unit problem, the first thing we need to do is make sure to come up with a set of 4 coherent bases. And that's what we're doing. The bases that convert to one another appropriately using the line to line, line to neutral, 3 phase, 1 phase, V to Z, you know, all that type of stuff. Okay, and I got 15 amps. And then for the Z base, there's another version of this equation in there, which is V ln base divided by whatever the I base is. And so we are going to have 120 volts. So the bases should have a unit. That's not to get confused with after you convert from an actual value to a per unit value. That's when you lose the unit. Okay? The base itself most definitely does have a unit. Because when you think about it, let's say you're going from actual units to per unit. You take your voltage at the source, let's say it's 110 volts, divided by the base, which is 120 volts, volts over volts, that goes away. That's how you end up with per unit. So if you end up with a base that has something funky going on with the unit, that's very problematic. Also, it should be a scalar, or should be a real value, okay? All of our bases are simply to scale the magnitude of the complex numbers, okay? So if we're never going to be getting rid of the degrees or the radians associated with the angle. So if you have 100 volts with an angle of 20 degrees, when you go to per units, it'll become 0.99 with an angle of 20 degrees. The phase is not going anywhere. Okay, so now we have our set of 4 bases. And another thing is, you can check to see if your bases are coherent, again, just by using basic Ohm's law and all that type of stuff, right? V base times I base should give you S base. I base should be equal to V base. I mean, we've already used some of those equations here anyway, but you see what I'm saying is that if you have a question about whether your bases work, you can just use the basic relationships between V and I and Z and S in order to test them. Okay, so now what values do we have? It asks us for the per phase voltage, the load impedance, the load current, and the apparent power. Okay. So what I'm going to do for those is let's line them up. So what are our actual solutions? Okay, so they were, the voltage is actually 120 volts with an angle of 0. The current, or I'll do impedance next. The impedance is 10 ohms. The current is 12 with an angle of negative 37. And the power is 1152 plus J864. Now let's write all of our bases. And I'm just going to put divide by, divide by, divide by, divide by. So our bases are 120 volt. Our impedance base is 8 ohms. Our current base is 15 amps. And our power base was 1.8 kilowatts. And that's the one place where you can have a little bit of leeway there. If it defines it, normally they'll call well, they may refer to the power base in watts or volt amps, but you can use either way in order to make either version to make the units cancel out. Technically, actually, they should never define the base in watts. It should always be in volt amps, because watts is the same as is equivalent to volt amps anyway. And then we get our per phase values. Sorry, per unit values. See, even I. So per unit values. And so the numbers that I got when I did this last time, obviously this one's going to be 1 per unit, or 100% of the rated value. The second one is going to be 1.25 per unit, or 125% of the rated value. The current is going to be 0.8 per unit with an angle of negative 37 degrees. That doesn't change. And then lastly, we'll have 0.64 plus J 0.48 per unit. So, I think that the key to these problems is just trying to visualize what's going on, not trying to skip too many steps. I think as you get later and later on into this course, you'll get a lot more familiar and you'll start calculating the per unit values a lot more quickly because you have other stuff to move on to. But at least for the first few times that you start using this, I would just be very careful and very meticulous in the way that you do this conversion. And then again, past like maybe a week and a half from now, they're just going to start giving you all the values in per unit to begin with. And we're going to stop using the actual values altogether. Okay. Next section actually has to do with our project. Energy efficiency. So our efficiency will be equal to the output power divided by the input power, which you can also define as the output power divided by the output power plus the loss. In many cases, yeah. In many cases, normally, unless it's otherwise described to you, the power loss is the I squared R loss along the line. That's it for that section. Not much to say. Okay, section 2.8. So, when we get into synchronous machines, when we get into transformers, there's going to be a decent amount of electromagnetics that we have to deal with. So we're going to we're going to revisit some topics that you probably talked about in earlier physics classes. We'll get into a little bit more depth with regard to those. And then we'll start building the base of how we're going to branch that over to understanding how transformers and synchronous machines work. So we know that current flow can affect, meaning EFF, ECT, cause a magnetic field. And the direction of the field depends on the direction of the current. Yeah. Electromagnetic. The only reason why we're going to be focusing on the magnetic portion is because for the synchronous machine and for the transformer, it's the magnetic field that's going to, it's going to allow energy to leap from one set of coils to the other. Okay, so equation 2.5.4. 2.54, sorry. So what do these mean? This is a closed line integration, which we'll talk about what that means again in a second. It's a way of looking at the amount of a magnetic field or number of flux lines that pass through a given path. H is going to be our magnetic field intensity. L is the path that we're considering. And I is going to be the current, or the sum of all the currents.
As vectors?
No, as actual values, because we're looking at this in a space, like a 2D space or 3D space. It's the current flowing through. Well, let's take a look at the example, and then I think it'll make things more clearly. Okay. So example 2.9, because what this example does, so you can see the current is the current flowing along the coil. So you shouldn't need to represent it as a vector, because the direction is simply represented by whether it's positive or negative or not. So what we're going to be doing is trying to analyze the magnetic field generated by this toroid, in this case like this. So example 2.9 is consider the figure of 2.21, which we'll draw. And so what's known we know that the coil has 25 turns, and the inside diameter is 5 centimeters. Outside diameter is 5.5 centimeters. And what do we want to calculate? Calculate the field intensity along the mean path length. So right, for this type of problem again, we're given a specific path. Well, first we're given a specific hardware setup, right? This toroid, we're shown how the wire is coiled, the number of coils there is, et cetera, what are the different diameters. And then they give us a path, which is essentially where we're measuring or where we're calculating, where we're considering what the magnetic field intensity is there through that path, and we're going to find the mean value for the magnetic field intensity through that path. So what does our figure look like? So we have the toroid, right, is essentially like a donut. Okay, we have our inside diameter. We have our outside diameter. We have our coil, which we have a wire coming in. Okay, this should be 25 turns. I probably did not draw 25 turns, but it was hard for me to count and draw at the same time. We have a current flowing in, and they tell us that current is equal to 3 amps. And then lastly, okay, our mean path is shown in black. Yeah, we have that. We're going to be Yeah, some of those values are embedded in the problem. They give you the constants that you need.
Just direct current.
Say it again?
Just direct current.
Yes. Yes. Okay. So the first thing we're going to do here is realize that a symmetry exists. As you can expect, right, this problem would be a lot more difficult if we had this irregular shaped toroid, right, if the coils weren't evenly spread throughout the circumference, if the path was not uniformly going through the center of the toroid or something like that, then, right, this problem would become one that would require very, very, well, I don't know how complex the calculus would be, but it's beyond my pay grade, let's say, in terms of being able to calculate what the intensity of the magnetic field would be along that mean path. However, for the example that's shown here, there will be, it's a simpler case. There's certain assumptions we can use, and we can represent all of those assumptions by referring to the problem as symmetric, right? We should be able to look at any slice along the toroid, right, and it should be acting in the same way because the coils are evenly spaced, the path is relatively in the same spot, et cetera, et cetera. So we know that the magnetic field intensity is constant. Along the path. All right. Next step. There's a couple values that we need, intermediate values that we need in order to calculate H. Step 2 is going to be to find the mean radius. And so that's going to be 1/2 the outer diameter minus the inner diameter. I think I included two times. That's a mistake. Hold on. No, that's right. Right? That would give us the mean diameter. In order to find the mean radius, we need to divide that by 2 once more. And so I have that. Hold on one second. That's wrong, sorry. I mixed two things together. Let's find this first. So here we have 1/4 times, what's the outer diameter minus the inner diameter? It's 0.5 centimeters. Right, so 0.5 divided by
5.5 minus 5 over 2.
well, I moved the 2 out to the, I made it 1/4.
Okay.
Yeah. So what's that? 1.2, this should be centimeters, so 1.25 centimeters. And we also need to calculate the, yes?
Wouldn't you want to add them if you wanted the average?
Yeah, I'm sorry. That's true. I have something, I'm trying to compare what I did in the book and what I did in the notes, and I should just try to do it on my own. All right, let's start over here. We don't need to recalculate that value. We just got it a second ago. So the mean radius was 1/2 outer diameter plus inner diameter divided by 2, which gave us 5.5 plus 5, so 10.5 divided by 2 will be 5.25. Okay. What got me thrown off here was that in my notes I combined together the length of the mean path and the radius, and it was all screwed up. Yes? This is what happens. This is what happens when I start skipping steps and I mismatch things together. Let's take a step back here for a second. Outer diameter 5 centimeters. Inner diameter 5.5 centimeters. 10.5 divided by 4, 2.625. All right, so this is right. Thank you. Okay, in meters. Okay, because eventually we're going to be doing everything in meters. That's going to be divided by 100, right? So that will give us 0.0265 meters. Nope. 2.5.
0.02625.
Oh, is it 2.5?
Yes.
My God, you're right. I'm sorry. It seems like when you start going down this path, you can do no right. You know, it's like when you're on a hot streak and like you can do no wrong. And then when you start making a mistake in a problem, it's like just no matter what you write down. I have 2.625 showing on my calculator, and I'm writing down something different. Okay. 0.02625 meters. All right. Good. Now, the length is going to be calculated in the same way as the circumference, right? So 2 pi r. So we will have 2 pi times 0.02625 meters. Which hopefully, I don't know why I have it in this other form. Hopefully it gives me the same value. Let me check it. I have 0.165 divided by... Yeah, it's the same. I don't know how I did it before. So calculate the mean radius as well as the path length. Okay. Step 3 is going to be to calculate the magnetic field intensity, H. And so the equation for that, this is taken from the textbook, the intensity of the magnetic field, and I apologize, I didn't write down exactly what the equation number is in the book, but actually I have it here. It's equation 255. number of turns times the magnitude of the current divided by the mean path length. And so this equation is going to apply only for this case, right, where this symmetry exists. Because we have the toroid, we have the constant or this right, the symmetric distribution of a magnetic field within the toroid. And you have a question? Come here. So the number of turns is 25. We have a current of 3 amps. And this right here ended up being approximately 165 meters. And so what that gives us is 454.5 amps per meter. Question now?
Shouldn't the permeability be in there?
The permeability is going to come into play when we talk about the flux linkages. Because the intensity, the permeability describes how the magnetic field is transferred, right, through the medium. The magnitude or the intensity of the magnetic field is independent of the permeability, but right, the flux linkages will be dependent on that, which is the next topic that we're going to discuss. Okay, that value also, just to backtrack a little bit, it can be constant or it can also be represented as instantaneous time varying. So we could put in 5 cosine omega t, and the magnetic field, right, would vary instantaneously along with the intensity of the current. So we would just propagate through the current in the time domain, not in the phasor domain, through to the end. Okay. Next topic. Flux and flux density. So flux density describes the density of the magnetic flux lines within a field. A little bit of a self-defining term there, but right, another way of saying that is it describes how many flux lines cross through a given 2D cross-section of a magnetic field. Right? So one example that I always see that's used if you're trying to calculate the magnetic flux density for sunlight, right? You could draw a circle on the ground, okay, and you could calculate the flux density based on the number of lines, right, that would pass through this circle on the ground. The amount of, or describe the amount of sunlight that falls on this spot. That's the density of the magnetic flux. Now, in reality, are there individual lines, right? No, they're not individual lines. It's not like we can pull out one line versus two lines. It's a continuous value, which we describe in terms of it's a way of representing the intensity of the magnetic field. So equation 256, right, tells us that the flux density is equal to the permeability of, in this case, we're going to assume that it's the permeability of open space, free space, times the magnetic field density. So this intensity, sorry.
We're gonna assume it's air. So are you using that?
Yeah. And it makes sense to use mu naught because in 99% of our cases, unless we're talking about an oil-filled transformer or something like that, right, it is going to be the magnetic field will be crossing, right, an air gap. Okay, so it's 9:17. We're going to have to go ahead and stop there. A couple different things. I do want to quickly assign the homework problems. So sorry I'm backtracking, but I'm just looking at all the problems all at once. I know you gotta leave. Give me one more minute.